Hello everyone, I am Fernando Méndez, a physics student, and today I'm going to tell you about work that Dr. Noguez and I do. Well, first a little resume of our work. Our study of the electronic properties of iron, selenium sub X, tellurium sub 1 minus X compounds for X equal to 0.0, 0.5, and 1.0 values using density functional theory demonstrates the significant influence of spin-orbit coupling effects near the Fermi level. Topological band inversion occurs around this energy when X greater or equal to 0.5, which is related to the topological effects described previously. The results also indicate that the Fermi surface undergo substantial change with varying X values, suggesting a phase transition due to the variation in the proportion of tellurium in the compounds. The motivation for our research is to understand the influence of spin-orbit coupling on electronic properties, primarily at energies close to the Fermi level in iron calchogenides. A number of interesting phenomena have been discovered in these types of compounds. One of them is Majorana bound states, which have been observed in materials with topological phases and have applications in quantum computing. Such is the case with Majorana 1, the microchip developed by Windows that promise to change the world of computing forever. The presence of Majorana bound states has been confirmed at each of the topological superconductor iron, selenium sub 0.55, tellurium sub 0.45. This fact was predicted by depth calculations with the addition of spin-orbit coupling effects. The appearance of a gap at energies close to Fermi level intuited by the topological phase. When considering spin-orbit coupling effects, this gap evolves into a topological band inversion. On the other hand, the superconductivity properties can be investigated by change in Fermi surfaces. In this study, we examine the physical origin of this phenomena. Our calculations were performed on quantum espresso using a plane wave basis set with an energy cutoff of 100 Rydbergs. We employed norm-conserving pseudopotentials and a semi-empirical D3 Grime functional. Fermi surface and spin-orbit coupling calculations were made on relaxed structures. Lattice parameters were tested by comparing with the previous calculations of non-relaxed iron, selenium sub X, tellurium sub 1 minus X crystals with X equal to 1.0, 0.5, and 0, showing an excellent agreement. Crystal structure and the first brittle one zone are shown in the next figure. Next, our results are presented in the following graphs. Electronic band structure in the gamma zeta path of the compounds iron selenium sub 0.5, tellurium sub 0.5, and iron tellurium is shown with and without spin-orbit coupling effects. The red circles indicate the weight of the d orbitals in the bands, while the blue circles show the contribution of the p orbitals. Adding spin-orbit coupling effects to the calculations induces energy gaps between bands, as indicated by the green square. The value of this gap is 8.93 milli electron volts for iron selenium, increasing to a maximum of 18.31 milli electron volts for iron selenium sub 0.5, tellurium sub 0.5, and decreasing to 10.73 milli electron volts for the compound iron tellurium. When X greater or equal 0.5, the main valence band contribution switches from d orbitals to p orbitals, resulting in a topological band inversion. Finally, the Fermi surfaces without the spin-orbit coupling effects are shown below with a color map indicating the Fermi velocities. An evolution of the surface as a function of the variable x is observed, where the quasi two-dimensional character of iron selenium compound surface is locked with the addition of tellurium, tending towards a more spherical surface typical of 3D materials. The isotropy is broken in the k sub x, k sub y plane, and the Fermi velocity increases in proximity of the C high symmetry point concerning iron selenium. Finally, the discussion, conclusions, and our future work. The inclusion of spin-orbit coupling effects modifies the dispersion along the gamma T path, resulting in the appearance of a spin-orbit coupling gap. In this region, an exchange between a valence band and a conduction band occurs for all compounds. However, only for x greater or equal to 0.5, there is a shift below the Fermi level, and a spin-orbit coupling gap evolves into a topological band inversion. Therefore, it's possible that iron selenium sub 0.5, tellurium sub 0.5, and iron tellurium compounds are topological superconductors. On the other hand, the spin-orbit coupling gap increases by 51.23% for x equal to 0.5 and by 16.77% for x equal to 0.0 relative to tellurium-free compounds. Similarly, it modifies the conductivity properties of the compounds, as reflected by the change in their Fermi surface, which indicates an increase in metallic character as more tellurium is incorporated. Similarly, the shift in Fermi velocities in the C high symmetry point direction reflects an increase in the interaction between compound layers. More later, to measure the superconducting gaps of a different sheets, a model of the effective interaction between electrons will be developed, based on the change in the Fermi velocity in different regions and sheets of the Fermi surface. In addition, the topological invariant C sub 2 will be calculated for each of these compounds and some intermediate cases to identify the proportion of tellurium that produce the transition to the topological phase. Thanks for your attention. See you at the 33rd International Congress on Material Research.